What is SSD? SSDs are storage devices that use NAND-based flash memory to store data. Unlike traditional hard disk drives, SSDs do not have any moving parts, which makes them more durable and reliable. SSDs are also faster than HDDs, and they are capable of accessing data more quickly, which makes them ideal for use in computers and other electronic devices. SSDs come in different form factors, such as 2.5 inches drives, M.2 drives, and UTWO drives. Each form factor has its own advantages and limitations, depending on the specific use case. Some SSDs are designed for high performance and are used in gaming computers, while others are more affordable and are used in budget laptops and desktops. Overall, SSDs offer many benefits over traditional HDDs, including faster speeds, improved reliability, and lower power consumption. E1L and E1S. E1L and E1S are both form factors for SSDs. These form factors were developed by the NVMe Working Group to address specific needs in the market. E1L is a long form factor for SSDs, which measures 110 mm in length. It is designed to provide high storage capacity and performance for data center and enterprise applications. E1L SSDs can support up to 32 NAND flash memory modules, which allows for capacities of up to 64 terabytes. E1L SSDs also support high transfer rates of up to 8 GB transfers per second. On the other hand, E1S is a short form factor for SSDs, which measures 80 mm in length. It is designed for use in space-constrained applications, such as laptops and tablets. E1S SSDs can support up to 16 NAND flash memory modules, which allows for capacities of up to 16 terabytes. E1S SSDs also support high transfer rates of up to 8 GB transfers per second. Both E1L and E1S SSDs use the NVMe protocol, which provides high performance and low latency for accessing data. They also use the PCIe interface, which enables faster data transfer rates than traditional SATA interfaces. What is EDSFF? EDSFF stands for Enterprise and Data Center SSD Form Factor, which is a specification developed by the NVMe Workgroup for SSDs that are used in data centers and enterprise environments. The EDSFF specification defines several form factors, including EDSFF E1L, EDSFF E1S, and EDSFF E3. EDSFF E1L is a long form factor for SSDs, which measures 110 mm in length. It is designed to provide high storage capacity and performance for data center and enterprise applications. E1L SSDs can support up to 32 NAND flash memory modules, which allows for capacities of up to 64 terabytes. E1L SSDs also support high transfer rates of up to 8 GB transfers per second. EDSFF E1S is a short form factor for SSDs, which measures 80 mm in length. It is designed for use in space-constrained applications, such as laptops and tablets. E1S SSDs can support up to 16 NAND flash memory modules, which allows for capacities of up to 16 terabytes. E1S SSDs also support high transfer rates of up to 8 GB transfers per second. EDSFF E3S is a small form factor for SSDs, which measures 32 mm in length. It is designed for use in high-density storage applications, such as hyperscale data centers. The E3S SSDs can support up to 8 NAND flash memory modules, which allows for capacities of up to 32 terabytes. The E3S SSDs also support high transfer rates of up to 16 GB transfers per second. Overall, EDSFF SSDs offer high performance, high capacity, and flexible form factors that can be used in a wide range of enterprise and data center applications. Differences between NVMe SSD and SATA SSD. NVMe SSDs and SATA SSDs are both types of solid-state drives that are used to store data in computers and other electronic devices. While they both use flash memory to store data, there are several key differences between NVMe SSDs and SATA SSDs. Interface. NVMe SSDs use the PCIe interface, which is designed for high-speed data transfer. SATA SSDs use the older SATA interface, which has a lower bandwidth and is slower than PCIe. Speed. NVMe SSDs are significantly faster than SATA SSDs because they use the PCIe interface. NVMe SSDs can offer read and write speeds of up to 7 GB per second, while SATA SSDs typically offer speeds of up to 600 MB per second. Latency. NVMe SSDs have much lower latency than SATA SSDs because they use a different command set and protocol that is optimized for flash memory. NVMe SSDs can handle more input-output operations per second than SATA SSDs, which means they can respond more quickly to requests for data. Price. NVMe SSDs are generally more expensive than SATA SSDs because they are faster and offer higher performance. However, the price difference has been decreasing as NVMe SSDs have become more common. Compatibility. NVMe SSDs may not be compatible with all systems, particularly older systems that do not have a PCIe interface. SATA SSDs are more widely compatible because they use the standard SATA interface that has been around for many years. Overall, NVMe SSDs are the fastest and most efficient type of SSD, but they are also more expensive and may not be compatible with all systems. SATA SSDs offer a good balance of performance and price and are compatible with a wider range of systems. Compare the speeds of NVMe SSD and SATA SSD in detail. NVMe SSDs and SATA SSDs both use flash memory to store data, but there are significant differences in the speeds between the two types of SSDs. Here are some details on how NVMe SSDs and SATA SSDs compare in terms of speed. Interface speed. NVMe SSDs use the PCIe interface, which is designed to offer very high-speed data transfer. PCIe 4.0, the latest version of the interface, can offer up to 16 GB transfers per second per lane, while PCIe 5.0, which was introduced in 2019, can offer up to 32 GB transfers per second per lane. In contrast, SATA SSDs use the SATA interface, which has a much lower bandwidth and is slower than PCIe. The maximum transfer speed for SATA LLL, the most common version of the interface, is 6 gigabits per second. Sequential read-write speeds. NVMe SSDs can deliver significantly faster sequential read and write speeds than SATA SSDs. For example, a high-end NVMe SSD can deliver sequential read speeds of up to 7 gigabits per second and sequential write speeds of up to 6.5 gigabits per second. In contrast, a high-end SATA SSD may offer sequential read speeds of up to 600 megabytes per second and sequential write speeds of up to 550 megabytes per second. Random read-write speeds. NVMe SSDs also offer faster random read and write speeds than SATA SSDs. Random read speed refers to the speed at which the SSD can access small files, while random write speed refers to the speed at which it can write small files. NVMe SSDs can offer random read speeds of up to 1 million IOPS and random write speeds of up to 1 million IOPS. In contrast, SATA SSDs may offer random read speeds of up to 100,000 IOPS and random write speeds of up to 90,000 IOPS. Latency. NVMe SSDs have much lower latency than SATA SSDs because they use a different command set and protocol that is optimized for flash memory. This means that NVMe SSDs can respond much more quickly to requests for data. The latency of NVMe SSDs is typically measured in microseconds, while the latency of SATA SSDs is measured in milliseconds. NVMe SSDs can offer latency as low as 20 ps, while SATA SSDs typically offer latency of around 100 ps. In summary, NVMe SSDs are significantly faster than SATA SSDs in terms of sequential and random read-write speeds, as well as latency. This makes them ideal for use in high-performance computing applications, such as gaming, video editing, and data analytics. However, NVMe SSDs are generally more expensive than SATA SSDs and may not be compatible with all systems. SATA SSDs remain a good option for users who want a balance of performance and affordability, and who are using systems that do not support NVMe.